Alright, we're back, and I actually haven't done anything at all. I drank a couple sips of beer, and I haven't done any of my research yet, and so we're going to do the research together. It's going to be great. So let's see if we can find some Chip-8, what would even be the word for it, like user manual or documentation? Let's try that out. Chip-8 technical reference, this sounds like a gooder. And there we go. This, I should just be using this. I'm just going to use this. This is a great document. Okay, so now we've got the better document than Wikipedia, what we should have probably been using right from the start. And this is going to help us out. And so we're on the subtraction method. And it does exactly what I expected it would do. I just hadn't heard the term borrow before. Cool. So if Vx is greater than Vy, Vf is set to 1, otherwise 0. Okay. Let's just make sure we kind of did this right. If the result is greater than 8 bits, 255, Vf is set to 1, otherwise 0. That's exactly what we did. The lowest 8 bits are kept and stored in Vx. Beautiful. We've kind of been doing the right thing. Okay, so V15 is now going to be, if we take the subtraction of these two things, and it's less than 0, then it's going to be 1, otherwise 0, and then we'll take the subtraction of these two and end it with OX00FF. Now, the results stored in VX. See, they went to great detail in the addition, saying how many of the bits are kept, all that kind of stuff, but they didn't do that for the subtraction. It's like, do I clamp it to 0, or do I just let it be the now new positive value? I think we're just going to go with the new positive value. So effectively we're doing the same thing as addition, we're taking the lower 8 bits and keeping them. Okay, that's cool. So we've got that done. Let me make sure I kind of did that right. Vx minus Vy. It's less than 0, that's 1, otherwise not 0. Cool. It's looking reasonable. On to the next instruction. If it's 6, if the last nibble, whatever you want to call it, the last 4 bits is 6, then we are SHR. I'm guessing that's a shift right. If the least significant bit of Vx is 1, then Vf is set to 1, otherwise 0. Is that what this one says too? Stores least significant bit and then shifts Vx to the right. Oh, cool. Yeah, cool. They both agree. Sounds great. So V15 is equal to just a byte of Vx, and that's what we're shifting, right? It's at least, and then we can end that with OX0001 to get the least significant bit, and then Vx shift right 1. Why is there this comma Vy there? What does Wikipedia say about that? It's just, it doesn't mention Vy at all, but the Y is sitting in there. And this one just has this, I bet if I read all this documentation it would tell me at the top exactly what that means. Chip-8 instructions, timers and sound, display. Oh, cool. Looks like there's some sort of built-in font between 0 and F. That's neat. Keyboard, registers, memory. This would have been a better place to start. I suggest if you are going to build your own Chip-8 emulator, you start with this. This looks better and more complete than the Wikipedia entry. This is what happens if you do your research first before making a video. But that's okay, we're doing good stuff. I assume this means that I can just ignore it, because this doesn't mention anything about Vy. Wikipedia doesn't mention anything about Vy except for having it in there, just trying to trick me. So we're going to ignore Vy, and we'll just say Vvx is equal to byte Vvx shifted by 1, and call it a day. Next is case 7, and case 7 is a sub n. Set Vx equals Vy. it's Vy minus Vx. If Vy is equal greater than Vx, then Vf is set to 0, otherwise. Okay. If Vx is greater than Vy, Vf is set to 1, otherwise 0. Okay, let me make sure I did this right. Subtracting, this syntax is weirding me out, and I need to replicate it the same way so that I'm not tricking myself. If Vx minus Vy is less than 0, okay, I had this backwards, it's my fault. What I should do is I should just implement the way they actually have it written. So if Vvx is greater than Vvy, right? 1, otherwise 0. Let's do it the way they have it written. And we're going to do the same thing for case 7, except we're going to switch these around. We're going to do Vy and Vx here. Same here, Vy, Vx. Now we've implemented sub n. Next, we skip from 7 all the way to e. Is that what happens here too? 7 to e. At least they're agreeing. Case e. E would be 14. And 14 is going to be doing a shift left. The most significant bit of Vx is 1. Cool. So V15 is equal to the byte, and I'm just going to kind of cheat on this. We'll end this with OX 80, right? That's the most significant bit. If that's equal to OX 80, then we return 1, otherwise 0. Let's take that whole thing. That should do the trick. So it's going to take the most significant bit. If that is set, then we return a 1, otherwise a 0. VBX is equal to the byte VBX left shifted by 1. Break on that. We've reached the end of our arithmetic logic unit, or whatever you want to call this section. And so if it's anything else, we're going to throw an unsupported opcode. Cannot fall from one case label to the next. Right, we need a break at the end of this. Just for fun, I'm just gonna try running this for now, just to see if some stuff is disappearing. Look at that, we've got a lot less opcodes that aren't being figured out. I know that we're not actually following the program flow yet. Oh, we're gonna get there, so it'll be good. Let's keep on going. 8 XYE. I thought I saw some 8s in here. Nope, I lied. I saw these 0080. So presumably we're going to get to those at some point. Jumps to machine code routine at N and N. This instruction is only used on the old computers on which it was originally implemented. It's ignored by modern interpreters. Well, this program's not ignoring it. It's got a bunch of 0080s in there. That's bogus. Okay. Let's try one different Chip-8 program to see if it behaves a little bit better. That's not the right folder. Let's go into here and try doing this Chip-8 picture. Ah, the emulator logo sounds good. That's a big string of text though, so I'm going to shrink that down and use that in here instead. Let's see if that has a bunch of 0080s. It has a bunch of 0000s. Why are they all using this? Modern interpreters ignore this. Obviously not written for modern interpreters. Okay, we're gonna have to implement this. Jumps to machine code routine at NNN. What does that even mean? Can I just assume it acts like a jump? No, it's it's totally bogus. That's what this is. It's totally bogus. And they're in there. 0080, 0080. Yeah, they're totally in there. What do I do about those 0080s? Is it that it's like a Chip-48? Super Chip-48 instructions. There's nothing in here that's 0080. There's some 00FFs. CN, SCV, nibble, SCR, SCL, and not much information on what those mean either. That's okay. We're just gonna keep on going, I think. What could that mean? 0080. That's okay. Let's finish this off and then see what it all looks like. And maybe it has something to do with the display or the font. There's probably somebody watching this saying it's obvious. Okay, ALU is done. We're going to skip the next instruction here. This sounds similar to code we've already done. Case OX9000. Skip next instruction if VX does not equal VY. That sounds very similar to this one here. Make sure that the opcodes are right. VX, VY, X is in the top, not the top 4 bits, but the 4 bits below the top 4 bits. Y follows. That looks correct. Cool. ANNN sets I equals to NNN. Okay, obviously I is not the program counter, so we're gonna make this work. It looks like I is perhaps a 16-bit address, probably used to access external memory. Okay, we'll fix that. A000, we'll say I is equal to opcode ended with OX0FFF. Okay, where did I use AI here? I use it in a lot of places, so we're gonna have to fix that. What I'm gonna do is I'm actually going to make this my program counter, PC, and I renamed all of my instances of I over to PC. And then, since I only really used I in one place, I can go and just replace that here. Now everywhere should use PC plus equals 2, so on and so forth. So I've kind of corrected the damage I did. My stack now pushes and pops with PC. Looks good. And now I is being loaded properly. I think we've implemented that. Looks good. Case OXB000. Jump to location NNN plus V0. NNN plus V0. Okay, so V0 is the first register, so we're going to set program counter is equal to the U short of opcode ended with OX0FFF, and then we're going to add to that V0. It doesn't say anything about setting VF based on an overflow or anything like that, so we're going to just run with it. C000 set EX equal to random byte ended with KK. That's cool. We're going to need some sort of random generator. Let's use the environment tick count to initialize this thing. And we're going to be set VX equal to random byte. So VX, which is going to be opcode ended with OX0F00 shifted by 8, is equal to generator.next byte. Next bytes. I'm just going to say next and that with the value k. This should work just fine. So opcode ended with OX00FF. That's the k portion. And we have to say that this is equal to a byte. Cool. That all looks good. Hopefully. The interpreter generates a random number from 0 to 155, which is ended with value kk. The results are stored in VX. See instruction 8xy2 for more information on AND. 8xy2. Okay, yeah, it's just a normal bitwise AND. Perfect. Display n byte sprite starting at memory location I at vx vy. Set vf equals to collision. So the interpreter reads n bytes from memory, starting at the address stored in I. These bytes are then displayed as sprites on screen at coordinates vx vy. Sprites are XORed into the existing screen. If this causes any pixels to be erased, vf is set to 1. Otherwise, it is set to 0. If the sprite is positioned so part of it is outside the coordinates of the display, it wraps around to the opposite side of the screen. It wraps around to the opposite side of the screen. Okay, so it probably falls off onto the next row. See instruction 8xy3 for more information on XOR, and section 2.4 display for more information on Chip-8 screen sprites. Okay, and if we go to display, just for fun, uses 64 by 32 pixel monochrome display. Looks good, so 64 is the x-axis, 32 is the y-axis. Supply some different modes. Chip-8 has a bigger resolution. Draws graphics through use of sprites. A sprite is a group of bytes, which are binary representations of the desired picture. Chip-8 sprites may be up to 15 bytes for possible sprite size of 8 by 15. Okay, so each bit of the byte is 1 pixel. Coordinates may also refer to a group of sprites representing hexadecimal digits 0 through F. These sprites are 5 bytes long, or 8 by 5 pixels. Below listing is each character's bytes in binary and hexadecimal. Cool. Okay, we can do this. So we're going to have to do a little bit of work because we're going to have to expand bytes, which contain 8 pixels, up to 8 bytes since our internal representation of display uses bytes. And so I'm going to start that in the next video.